going to walk through another example of using comparable. So we're going to write a new set of classes, and these classes are going to represent a playing card, like you would play a game with, hearts with the various suits, hearts, diamonds, clubs, and spades, and various values, ace, 2, 3, 4, 5, 6, 7, 8, 9, jack, queen, king. And then we'll also define a class to represent a deck, which would be a collection of cards. And we're going to define a natural ordering of cards, meaning that our card class is going to implement comparable. So let's take a look at what this would look like. And we're going to start by just writing the classes, and then we'll add on the comparable part after that. This will also be a good reminder about enums, because we're going to use some enums to define our card class as well. So let's take a look at what our card class is. Well, if we think about what a card is represented, so again, anytime you write your own class, you want to start by thinking about what the instance data variable should be. Well, if you're thinking about a card, you have kind of two pieces of information. You have the suit and the numeric value, or the value of the card. So suits, we have four choices: hearts, diamonds, spades, and clubs. And for values, we have, 2 through 9 for the numeric values, and then we have jack, queen, king, ace. So because these are pre-defined sets of things with a finite set of values, enum is a good choice to represent that. So we can create two enums. The first will create a public static enum called suit. And again, remember that enum naming conventions follow the same conventions as class naming. But the value naming follows the naming conventions for constant. So my four suits are going to be spades, clubs, hearts, and diamonds. And that's going to be just a pretty simple enum. Now, I could put this in its own class, suit.java, or I could keep it as an inner enum inside the card class. There's no real convention about that. It's kind of subjective. You have to decide whether you think logically it makes sense to kind of be on its own, or whether it's only going to be used sort of as in relation to the card class. You also can make that decision based on how big the enum gets. So enums that get very big and complex, sometimes it makes sense to move them into their own file. So you want to think both about sort of the logic of it and also just sort of the mechanics of it. In determining whether to keep it inside a class or put the enum in its own class. I'm going to choose to keep a suit inside this class because I think a suit really only makes sense as something that describes a card, and also because it's a pretty simple enum. Now, the other aspect that describes a card is the value of that card, the numeric or face card value of it. So I'm going to write another enum for that, and I'll just call it value. And for this one, I have a lot of different values, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I've got jack, queen, king, and I've got ace. Those are all my values. Now, I might want to have another piece of information represented with each one of these values. An obvious one would be the numeric value of each one of these cards. So what I can do is I can define a private instance variable called value and associate that with each one of my enum. I'm going to say values, which is a bit confusing because I've called it value, but with each one of these enum value options. So I'm saying the numeric value of each one of these choices is going to be associated with that enum value. And so all of those, the numeric is just the same as the word, but for our face cards, those are worth 10. And we'll say that our ace is worth 1, although I know in some places in some contexts ace is worth more, but just to keep things simple, we'll say that the ace is worth 1. How we initialize those values is we create our enum constructor, and we take that value in, and we just initialize it. Now, because that value is private, we also want to create a public getter where we return that value. So this is going to be my value enum. Now, again, thinking about whether this should go inside the class or in a different class, it's a little bit longer, obviously, than suit, so that might make me inclined to put it in another class. However, I think similar to the suit enum, this really only makes sense in the context of a playing card, so I'm going to choose to leave it inside the card class. It wouldn't be wrong to put it in its own class, and two different people approaching this problem might do it differently. I'm going to make that decision, and again, there isn't one kind of right or wrong answer for that. Now, you might think of other characteristics that you'd want to associate with different card values. For example, you might want to just have an easy way to tell if something is a face card, right? So a lot of times special things happen for face cards, so you might want to know that. If you wanted to know that, you could just add another piece of information that's associated with each one of your enum values. So all of these are not face cards. And these ones are. And then, of course, you would add that information to your constructor. And add a getter for it as well. So when you create a variable of a value type, this enum, it's going to have these particular characteristics associated with it. And when that object, when the enums are created, that's when these values get put into the constructor. Okay. So there's just a quick little review about enums. So now let's actually write the card class. So those are our defined enums. And now let's write the card class. So again, in thinking about our instance data variables, the reason we wrote those enums is because they're going to describe the characteristics of a card. So we're going to have a suit for the card and a value for that card. And then we will set up our constructor, which takes in the suit and the value and initializes those instance data variables. Next up would be getters and setters. Now you might think about creating traditional getters and setters, but if you're really thinking about a suit and the value enum as just sort of being more internal mechanism of knowing how a card works, instead of just having straight getters to return the suit and to return the value, you might think about modifying those a little bit. So when we think about the suit, it actually probably does make sense to just have a straight getter for the suit. So I'm going to say, getter for suit that just returns that suit. But for value, instead of just returning the value object, it might make more sense to just return the numeric value, which would be value.getValue. And it might also make sense to say, well, is this card a face card? And for that, we would say return value.isFaceCard. So we're sort of encapsulating the value enum, kind of hiding that functionality inside of card and just providing the outward facing information that a user of the card class might want. So we're sort of keeping that value kind of internal. Okay. Again, you might think of reasons why you want to just return the actual value object, but most likely these are going to be enough for what you want to use. And these are, again, the more logical things you want to know about a card. Now, I'm going to choose not to include any setters. I'm going to say that once you create your card, you can't change it. There's obviously you could include setters as well. And if you did so, you would include setters for probably the type suit and type value. Next up will be toString. So let's write our toString. And I think for our card, we can just return the value plus the suit. So this will be like the ace of spades, for example. Remember that the toString of an enum is the actual value. So it's going to be, spades in all caps or jack in all caps. If you wanted to override that, if you wanted it to be, spades with just a capital S, you could override the toString inside of the enum. So for example, that might look like this. Maybe you'd have to have the value associated with it and then create that value, create a I'll call it display string, and then you would return that display string. And of course, you'd have to set up a constructor to initialize the display string in each one of these values. So I'm not going to do that, but that's just a little reminder of how you can have the toString output of your enum not be the all caps actual value. So you just basically override toString and you create sort of an output friendly version of each one of the values. Okay. But again, I'm not going to do that for our purposes here, but I just wanted to show that quickly. Okay, so that's going to be our toString. And the last component we put into every class we write ourselves is an equals method. So let's put in an equals. Remember, public Boolean equals always takes in a parameter of type object because we are overriding the version of equals that we inherit from the capital O object class. Because the parameter is object, if we want to compare, what the purpose again of this equals method is to compare the current card to some other card to see if they're logically equivalent. But we have to have the parameter type be capital O object because we are overriding the version that we've inherited. So internally to the method, I need to make sure that you're actually giving me a card object, and then I have to cast it to that type to make sure I can actually, the compiler will treat it as that type. So first we say, well, is object an instance of card? If so, I'm going to do some comparisons. If not, I'm just going to return false, because if you give me some other object, it's not going to be equal to a card. So I'm just going to return false. If it is an instance of a card, I need to tell the compiler to treat it that way. So I'll create a local variable other card, which will just be object cast to type card. And now I can go ahead and just say, well, two cards are going to be equal if they have the same suit and the same value. So I can just return this dot suit equals other card dot suit, and this dot value equals other card dot value. And that will compare whether the two cards have the same suit and the same value. Now remember that for enums, you can also use the double equal sign. That's okay, because the way an enum is defined, there are only this pre-specified number of values. So you're allowed to compare enum variables with double equal sign or equals method. It returns the same value, but I like to just use the equals method because it just goes along with our general practice of using the equals method for objects and only using double equal sign for primitives or for when we really do care about aliases rather than equality, logical equivalence. So that so far is going to be my card class. So now let's think about the deck class. So if I want to represent a deck of cards, I could define a list that holds card objects and call it the deck. And I could then create a constructor. And maybe in my constructor, I'm going to take in a parameter telling me whether I should create an unshuffled deck, which would be sort of an ordered deck, or a shuffled deck, which would be a deck of cards with, ordered, however I decide to order them. Okay, so I'm going to leave that there. We're going to come back to that in a moment. But first, what we have to do is we have to actually fill up the deck. So what we can do is we can create a new array list of card objects. Remember, when using generics, putting the card on the right-hand side is optional. That would also be allowed. But if I don't put the type, I do still need to put the caret brackets. I tend to put the type in so that I don't forget the caret brackets, because either way, you definitely need those the angle brackets there. And then I'm going to have a method to fill up the deck. So I'm actually going to write this as a private helper method, because I think it's possible that I might reuse this at other times. Maybe we create a deck object, and then at some other point we want to basically create a whole new deck out of that object, right? Put a whole new set of cards into the deck. So I'm going to create this as a private helper method that could be reused throughout my class. And what I'm going to do is when you're saying it's time to fill the deck, we're just going to clear out the list to make sure there's nothing in it. This would make sense if, again, you were using it at some point later in the program. And now what I want to do is I want to create 52 card objects to put inside the deck. Now, how can I create one card of each one of my suits and each one of my values? Well, I can just use a loop to go through all the possible values and to create those cards. So what I can do is I can say, okay, for every suit in the suit enum, and remember that what you can do to get all the possible values is invoke the values method on an enum. So a couple things going on here. First of all, I have to access card.suit because I did choose to make suit a nested enum. If I'd put it in its own class, I could just access it directly. And then remember that values will return a suit array of all the possible values. So I'm going to use a for loop to cycle through those. So for each suit, now I'm going to do the same thing to go through each value. And then what I'm going to do is I'm just going to create a new card with that suit and value. And add it to my deck. And that will fill up my deck. Okay, so there is an initial constructor. Now, other things we might want to think about for this deck is what functionality do we want? So, well, actually, we're creating a class. So we've thought about our instance data variables, our constructor. We next want to think about getters and setters. Maybe we decide it doesn't make sense to return the list. We want to keep that internal, keep that private. So we're going to not provide a getter or a setter for it. ToString, we probably do want to have a ToString. So let's override our ToString. And what we can do here is we can just have the text representation be a printout of all the cards in the deck. So I'm actually going to use a string builder because I'm going to be doing a lot of concatenation. And I'm just going to say for every card in the deck, let's append to the string builder the card's ToString, the string representation of that card, and then a new line. And then we'll return the string builder ToString. Okay, so this will give us a text representation of all the cards in our deck. Other methods we might want to implement would be, okay, so sorry, let me go back to writing a regular class. So we've got instance data variable, constructor, getter, setters, which we chose to omit, ToString. Next up would be an equals method. We might think about writing an equals method to allow you to compare two decks. Maybe we think that's not necessary. If we did think that was necessary, it would actually be pretty easy to implement. We'll start with our setup same as every other equals method with checking the type. We can actually just return whether the current deck, which is an array list or a list object, is equal to the other deck, that deck. And what this does is it relies on the equals method as defined in the list class, or in this case, the array list class, to say, okay, how are two array lists equal? Let's let the array list figure that out. And of course, at some point, the array list is going to compare the elements inside the array list. And in doing that, it's going to jump back and use the equals method of the card class. So we have, again, this idea about each class being in charge of its own functionality. An array list knows how to compare two lists. The card class knows how to compare two cards for equality. So each class kind of is in charge of its own functionality. Okay, so that would be our equals method. So now we can go ahead and add the methods that are specific to this particular class. An obvious one is going to be shuffle. So you might want to shuffle the deck. And there is a method in the collections class, the Java collections class, called shuffle, which is really great. It'll just shuffle up a list, so we can actually just use that to shuffle the deck. We can now also go back to our constructor and say, well, okay, if you told me that you wanted the deck shuffled when you created it, I'll go ahead and call that shuffle method. If not, we're going to leave it as it was created. Okay. Another obvious method is going to be deal. So this, we might return a card object, and perhaps we'll also print it out. So let's first of all make sure that there's something left in the deck. Let's make sure the size is greater than 0. And if it does, we can take the first card off the deck. And maybe we'll print it out and then return it. And if it's not if the deck is empty, we'd have to decide what we want to do. Do we want to throw an exception here? Do we want to return null? Want to give some sort of error message? I'm going to just choose to give an error message and return null. You'd have to think about whether you wanted to throw an exception instead. So there's my deal method. So let's start with those. And then we're going to come back and add comparable. So let's just go over to our tester program and we're going to create a deck of cards. It's going to be unshuffled at first. Okay. And then we'll print it out. Let me run this. You can see that once it runs. Come on, Eclipse. Sorry, let me pause this. Eclipse has a hard time catching up sometimes. So that actually wasn't a Eclipse problem, that was a programming problem. Did anyone catch the mistake I made in the deck class? So I forgot to do one very important thing. I created my new array list and I wrote a method to fill up the array list, but I didn't actually invoke it. Okay, so I have to actually fill up that deck before I can shuffle it. So there we go. So now let's try it. There we go. So that is our deck of cards. You'll see 52 printouts, and they're going to be in the order we created them. So we went through each suit, which the suits are ordered spades, clubs, hearts, diamonds. So you'll see spades, clubs, hearts, diamonds, and then they'll go through the order of the values that we created them in. So 1 through 9, and then Jack, Queen, King, Ace, and Ace. And actually there is a 10. Sorry. Wow. Wasn't thinking there. Okay. So if we want to have a shuffled deck instead, we could do that. And when we create that, you'll see that these are all shuffled up. So the order of the cards is all shuffled. Now, what if we also want to be able to sort the deck? So in addition to shuffling it, let's say we want to be able to sort it, to put it back in order. How can we do that? Well, we'd like to be able to just use the functionality provided to us in the collections class. So just like we used a shuffle, we'd like to have a sort. Okay. However, we get an error there because the problem is we don't know how to compare two cards. So anytime you want to sort something, whether it's an array list, an array, you have to know how to order the elements in that collection. You have to know how to compare them. If we're sorting numbers, well, we know how to sort numbers. We just put them in numeric order. If we're sorting strings, we know how to sort strings. We just put them in alphabetic order. But to sort cards, we don't know how to do that. So we have to define it. We have to define what's called the natural ordering of that class. So let's go back to card, and we're actually going to say that our card class implements comparable, but not just comparable of anything, comparable of other cards. So I'm going to define the natural ordering of cards by specifying how you compare two card objects. So what that means is I'm now going to write the compare to method, which looks like this. So public int compare to, and because I've used generics, which is the appropriate thing to do, up here in the class header, comparable, and then put the type, the class name or the type inside of those angle brackets, in this case card, I can have the parameter of my compare to method be card, which is good. This is the appropriate, the recommended and conventional way to use generics and to write the compare to method. So what I want to do now is I want to compare two cards. So what I have to decide is what is the ordering I want to define for cards. What should their natural ordering be? Well, there's kind of two obvious choices. We can first order by suit and then by value, or we could first order by value and then by suit. Let's first order by suit. So what we can do is, again, we're trying to compare this current card to some other card and just say what makes those two cards. How would I order just those two specific cards? what makes one card less than, greater than, or equal to the other card. That's all this compare to method does. The compare to method itself doesn't sort anything, doesn't take a whole collection of cards and order them. All it does is it says, if you give me two cards, a current card, which is going to invoke this method, and some other card, which is going to be sent as a parameter, I'm going to tell you which of those two cards is bigger, smaller, or if the two cards are the same. That's all the compare to method does. So you're just defining how to order two objects of this type. And that's what's defined as the natural ordering. Okay. So what I can say is I want to say, well, first of all, let's see if they have different suits. So if this dot suit is not equal to other card dot suit, we're going to then order by value. Now, the nice thing about enums is that they, by definition, have a natural ordering. The natural ordering is the order in which you define the values. So the natural ordering for suit is spades, clubs, hearts, diamonds. The natural ordering for value is, 1, 2, 3, 4, 5, and so on. So what I can do is I can just say, okay, if these two cards have the same suits, then I'm going to order them by value. So I'm going to return this dot value compared to the other card's value. But if they have different suits, sorry, that's if they have the same suits. Sorry, I confused myself there. This is what I want to do if they have the same suit. So if the current card is, the Jack of Diamonds, and you give me the Nine of Diamonds, well, I can't order those by suit. I can't compare those by suits because they have the same suit, right? So the suits are equal. So in that case, I'm going to return the comparison of the value. But this else means the suits are different. In that case, I'm just going to compare the suits. Okay, so again, this is kind of a common setup. You say, if one attribute is the same, compare by kind of the second level attribute. But if that top level attribute is equal, then return that. You also might, see this written where if this dot suit is not equal, then you would return the suit, otherwise return the value. So you might see these if and else reversed. There's no convention. It kind of just, however you think it best makes sense, that's how you can write it. But this sort of nesting of compared attributes is very common for the compare to method, because oftentimes there's more than one attribute that you need to compare something, right? If you have a whole group of people, you might sort them based on last name, but if two people have the same last name, then you go to first name. Right? If you're sorting a whole bunch of books, you might sort them by author, but if if two books have the same author, then after author, you sort them by title. Okay. Now, again, remember, compare to doesn't actually sort anything, right? It just defines the natural ordering of two objects. It just says what makes one object less than, greater than, or equal to some other object. And it does that by comparing the attributes of those two objects, comparing the attributes of this to the attributes of the other. And it's going to return either a positive number. If it returns a positive number, that means the current object, this, is bigger. Or a negative number. If it returns a negative number, that means the parameter object is bigger. Or it's going to return 0, which means that the two objects are equal. Are the same. Not one is not bigger or smaller. Okay, so that's all the compare to method does. If you'll notice now in DEC, our compiler error has gone away. We are allowed to now sort this collection. So now I can go back to my card tester. Let's have a shuffled up deck, and then let's sort it. And let's print it again. Okay, so here is the shuffled up deck at first. You see it's all shuffled up, and then after sorting, it goes back to arranged by first by spades, right? Because we said the ordering is defined first by suit, and then internally it's defined by the value. So 1 through 10, Jack, Queen, King, Ace. And then the clubs in that same value ordering, and then the hearts, and then the diamonds. Okay. Now, one really other important thing to note about compare to is note that we don't actually ever invoke it. I don't have in my code anywhere card.compare to other card. The compare to method is invoked by the sorting method. So when you use the sorting method of the collections class or of the arrays class to sort arrays, internally, that method that's implemented internally, that's what calls compare to. But you invoking that method, you never call compare to. It has to be there. You have to write it, but you don't call it. Now, if you were to write your own sorting algorithm, if you were to write a sort, a method to sort things, then you would invoke compare to. But if you're just using existing sorting methods, which is of course the easiest thing to do, then you never actually invoke compare to. Again, it's got to be there. You have to define a natural ordering, but you won't ever actually invoke it. Okay. Now, this could be one natural ordering. Of course, we might have made a different ordering. So someone else might have come along and said, well, actually, I think the natural ordering of cards should first be by value and then by suit. So I want all the ones together, all the twos together, all the threes together, and so on. In that case, I would say, okay, well, if the values are different, and I'll write it the opposite way this time just so you can see what that looks like. So if the values are different, then sort them by value. But if the values are the same, then you need to go to the sort of next characteristic, the second characteristic, and return that, which is the suit. So this is another possible ordering. So now if we run our main method again, what do I have? Extra parens. Okay. If we go back and run our main method, you'll again see that first the deck's all shuffled up, and then after we sort it, it's got all the ones together, all the twos together, all the threes together, and the suits are ordered by, spades, clubs, hearts, diamonds. Now, we could also, in our case, let's say we wanted ace to be low instead of being high. We could just move that value to the beginning of the enum list and run this again. And now you'll notice that in the sorting, all of the aces come first. Okay, so for enums, the natural ordering of an enum is, again, the order in which all the values are defined. So that's how you can choose the ordering for your enum. And you can, of course, choose, again, the ordering of your object by defining compare to. Now, it's very, very common inside of a compare to invoke equals methods and to invoke compare to methods. So that's almost always going to happen. If you're comparing two objects, you're going to probably need to compare the characteristics of those objects. And to do that, you'll most likely have to invoke compare to on the instance data variables of those objects. So it's very, very common to invoke compare to inside of your comparable inside of your compare to method. If you're comparing primitives, you might have a conditional instead, because of course we can't invoke compare to or any method on a primitive. So if you had primitive values you were comparing, you could either use it compare with conditionals, less than or greater than, relational operators and conditionals, or you could use the integer.compare method where you send into integers and so on. Okay, so those different options with primitives. But if you're comparing instance data variables that are objects, including enums, then it's very common to invoke compare to. The other thing you might see is instead of invoking equals, you might see someone invoking compare to and testing whether that's 0. There are some cases where, I might need to add an extra parens here. There are some cases where two objects can be equal, meaning the equals method returns 0, but compare to does not return 0. If you invoke that on the same two objects. It's rare, but it can happen. And so if you wanted to account for that possibility, then in your compare to method, you would test whether the compare to is equal to 0 as opposed to testing equals. But if you know that the classes you're dealing with, if that isn't the case, which is most classes, then using equals is going to be the same as using compare to equals 0. Okay. So there's a little example. Let's do one more thing in main. Let's actually create a little hand for ourselves. Hand of cards. And we'll say we'll deal 5 cards. Actually, let's shuffle the deck before I do this. And what I'll do then is I will add to my hand a card that's dealt from the deck. Then let's print out our hand. So I dealt these 5 cards, 5 of hearts, Queen of clubs, 3 of hearts, 10 of diamonds, 8 of spades. And of course, I can now also sort my hand because you can send any list into collections.sort as long as the objects held in that list implement comparable. So I can now sort my hand, and let's print it out again. And you'll see that now my hand is sorted: the 2, the 4, the 6, the 7, and the queen. Okay, so there is another example of writing classes and also using comparable and using enum. So hopefully this example kind of helps sum up a bunch of things. But the main thing I wanted to focus on, which we didn't get till to the end, but hopefully this really was a good example of implementing comparable and the compare to method and how that method is used, how it's implemented, and then how it's used. Namely, it's used whenever you invoke a sorting algorithm.